Hi, this is section 4.6, and it's called Modeling Direct Variation. You might want to go right now to page 253, and we're going to start off with vocabulary. So before we actually get into the technicals of what direct variation is and the actual definition of it, let me just give you a real-life example of direct variation. And it could be something like this, where I say, let's say it was summertime and I saw you out and about and I said to you, hey, I'm going on vacation and I need someone that will mow my lawn when I'm on vacation. And I will pay you $20 if you mow my lawn. It only takes an hour. Would you be willing to do that? Well, I suspect most of you would be like, sure, for an hour of work, 20 bucks, I'll take it. Okay? Well, an equation that would demonstrate that situation would be here, where y is the dependent variable, it's the money that you would earn, and x is the independent variable, it's the number of times you mow. Okay, so I think you would understand this situation pretty easy, where, hey, if Mr. Lemansky's only gone a week and I mow one time, I'll make 20 bucks. If Mr. Lemansky needed me to mow the lawn twice, he'd give me 40. 2 times 20. If he needed me to mow it 3 times, he'd pay me 60. If he needed the lawn mowed 4 times, he'd give me 80, and so on. This is an example of direct variation. Now, in the book, when you look at page 253, at the top it says 2 variables x and y show direct variation provided y equals ax and a is not equal to 0. Okay, that sounds very technical. I'm going to try to explain it in my own way. X and y show direct variation when we have an equation in slope-intercept form, which you do here, in which the y-intercept is 0. So you notice here, that's what I have. I have y equals, remember, slope-intercept form looks like this, y equals mx plus b. Well, you can see in the situation that I made up, the slope would be 20, but there's nothing being added to this. Well, that means that my y-intercept in this case would be 0. I'm not getting a tip. Mr. Lemansky's going to give me $20 every time I mow the lawn, but there's not any extra money coming for something else. This situation would be direct variation. So when the y-intercept is 0, in other words, the b value is a 0, which means you actually wouldn't even see it, this is what an equation looks like when we have direct variation. Okay, this number here, 20, now I'm giving you 20 bucks every time I mow the lawn. This number has a special name. It's called the constant of the variation. And in other words, in my lawn mowing example, the constant, I should spell right here, the constant of variation is 20. In other words, every time you mow my lawn, you're going to get an additional $20. So that's what direct variation is. It's when you have an equation in which the y-intercept is 0, which means in slope-intercept form, your equation basically is just y equals mx. You don't see anything being added, it's 0. So I hope that real-life example makes sense. That's why at the top of page 253, and in that second little tiny paragraph, the last sentence says the equation y equals x plus 5 is not an example of direct variation. Okay, this is not an example right here, and the reason it's not an example, as you see, my m value equals 1, but my b value is not 0. The b value has to be a 0 if I have direct variation. Okay? So again, let me just get this out of the way. Let me erase what I have so you can read that next little blurb I put. Okay? So in other words, again, y equals mx is what direct variation looks like, because that's what the equation looks. So in other words, the equation would look like this. Okay, this is a direct variation equation at slope-intercept form where the b value is 0. Again, here would be an example of something that's not direct variation. 2x plus 1, you notice the b value must equal 0 to have direct variation. I wanted to show you this also to show you on a table how I can see direct variation. I want you to notice on my table here, do you notice that if I double my lawn mowing, I'm going to mow twice instead of once, I doubled my pay. If I tripled the amount of lawn mowings, I tripled the pay. If I quadrupled the amount of lawn mowings, I quadrupled the pay. Well, that doesn't happen here. This is not direct variation. You can see it in the table. If I double x, do you notice y did not double? So this would certainly not be direct variation because you ought to have that relationship when you have direct variation. All right? And of course, I told you that 20 in this case was the constant of variation. All right, so in the bookwork, they're going to ask you, if you go ahead to page 257, one thing they're going to ask you to do in questions like 3 through 8, they're going to ask you to tell if the equation represents direct variation or not. If so, identify the constant of variation. So to tell whether an equation is direct variation or not, it's very simple. We just have to quickly decide, is this equation in that form? Okay, now obviously this is not written in that form, so the first thing, let's see if I can rewrite this equation into slope-intercept form where my b value is nothing. So that's what I'm going to try to do here. I'll take away x from each side, which gives me negative 3y equals, that'd be negative 1x, and I'll divide each side by negative 3, and I get y equals 1/3 x. Well, do you notice this is definitely in this form? I have y equals 1/3 x plus nothing. My constant of variation right now is 1/3. You don't actually have to make a table, I'm just showing you again. If I did make a table of this, if I plugged in 1, I'd get 1/3. If I plugged in 2, I'd get 2/3. If I plugged in 3, I get 3/3. Notice, if you double x, you doubled y, 1/3 doubled is 2/3. If you tripled x, you tripled y, triple a third's 1. This is definitely a table of direct variation. Okay? So again, my constant of variation, I'm just reiterating, was 1/3, and this is direct variation because this equation does look like y equals mx. There is no b value. Well, there is a b value, it's nothing. Okay? In number 8, let's see if this is direct variation. I got to solve for y. I'm trying to figure out again, does this equation take this form? Well, let's try that. I got to solve for y, which means I got to divide each side by 1.2. When I divide each side by 1.2, and I'm going to break this up into separate fractions, I get 2.4x over 1.2 plus 6 over 1.2. That gives me 2x plus 5 equals y. This is not direct variation. And the reason is I have a b value that's not 0, okay? So my slope is 2, or my constant of variation is 2, but I need a b value of 0, and I have a b value of 5. This is certainly not direct variation, okay? Not direct variation, and you can see that in the equation. They are going to ask us to graph direct variation equations, and actually this is incredibly easy to do because my b value is 0, like in number 18, y equals negative 3/2 x. Now there is no plus 0 at the end, so I'll just put plus 0. First of all, as you might notice, this is definitely in slope-intercept form. Y equals mx plus b. Just going to write that in there. So my first thing is, you can tell my b value is 0. Go ahead and graph that point. My slope is negative 3/2. That means I'm dropping 3, running 2, so I can kind of illustrate that real quickly, and I will. and you can see I am dropping 3 and running 2. I'm dropping 3 and running 2. You can see that there. I guess I could even think of going left 3 and up 2 and create another point. So you can see I'm getting 4 points there. Let me just get that out of there. There we go. Okay. And now all I need to do is draw a line through those points, put arrows at the end. I just graphed y equals negative 3/2 x. Very simple to graph that. Let's also go to 29 and talk about that. Given, it says in the directions, given that y varies directly with x. Okay, now those first words are important. Okay, I'm actually going to write that out. Okay, when you see that y varies directly with x, as soon as you see that phrase automatically tells you, it automatically means that your equation must look like this. Okay? So I know right now that in number 29 my equation must look this way. It says, use the specified values to write a direct variation equation that relates x and y. Okay, well, in number 29 they tell me that x is 3 and y is 9. So what I'm going to do is I'm going to take 3 and plug it in for x and y and plug it in for 9. I need to find out what this constant of variation is. Well, that's easy. Just solve for m. Divide each side by 3 to get m by itself. M equals 3, so my equation must have been y equals, m was 3, y equals 3x. There's my equation for number 29 if x was 3 and y was 9. My constant of variation had to be 3. Okay? And that's all we have to do on each of the problems from 29 through 37. You'll notice in questions 26 and 27, they're going to ask you if the table represents direct variation. Okay, that should be kind of easy now to determine. If, and I can even show you on your calculator how you could actually even do that. I guess I can do that in class tomorrow. But remember, direct variation has to have the following pattern in a table, right? So if I'm doubling one amount, I should be doubling or whatever to get to the next and so on. You can always tell if you have direct variation by using that method, I guess you could say. All right? So that should help you with number 26 and 27 in the book. That's the end of my video. If we have questions, we can go over any further questions you might have had on this in class tomorrow.